So we left off, right? We were talking about continuity on intervals, right? And all we really said is it's continuity on intervals is really no big deal. We know that how to define point continuity. We've got these three criteria for continuity at a point, and we said that on an open interval, the function is continuous on the open interval at every point on the open interval where all three of these conditions are met. And so what we would be looking for then on an interval are the select few places, presumably, where maybe the condition isn't met. We're finding the individual points where, you know, where one of these three or more than one of these three conditions fail to be met. And so that would be a discontinuity. When we want to look at continuity on a closed interval, remember this is going back to, I think it might have even been last week, we introduced this concept of continuity from the right and from the left, right? Where we, in order to deal with the endpoints of the interval, remember what we said about that, we only have to be able to approach the endpoint, the left endpoint from the right and the right endpoint from the left. For it to be continuous from the right or from the left. And if we add that one little concept to it, then we can expand our idea of continuity all the way up to continuity on a closed interval. More simply, we know what our rule of thumb is. If I could put my pen down on the board at point A, where x equals A, and take it off only when I get to x equals B, then that's continuity on that closed interval, right? Okay, give me 1 to 5 on all that stuff. Are we pretty good on that? Okay, good. All right, so then this is the problem. We were looking at some examples of problems where we want to state the intervals over which the function is continuous. And this is a pretty good one to look at because it involves a square root, and this can be a little tricky. So we decided here, right, what the only red flag that pops up for this function is that it's an even root, right? We can't take an even root of a negative number. So that imposes a condition on us. If we can't take an even root of a negative number, then that means that the argument of that square root, you know, whatever's inside the square root, has to be non-negative, has to be greater than or equal to 0. And so now we can kind of just switch into algebra mode, and we're just going to solve that algebra problem to find the domain of the function, right? Because that's the condition that needs to be true. Okay, so then we were going about the process of just solving this thing. Okay, well, we could either subtract 4 and multiply by -1, which flips the sign, or we could just add the x squared to the other side and then reverse the direction of the inequality. Either way, we end up here, okay? And then this is kind of where we left off. We're trying to isolate the x, and so we square root both sides. What is the square root of 4? Say it again. Right now I'm just asking, what's the square root of 4? You say plus or minus? Oh, okay, sorry, these masks messed me up. Okay, it's actually not. The square root of 4 is 2, right? When we ask for a square root, we're asking for the principal square root, and the square root of 4 is 2, okay? But the plus or minus is an important part of this. What Ethan's getting at is that if we're solving an equation like this, if we know that x squared equals 4, then we know that the answer is, the solution is x equals plus or minus 2, right? But remember where that comes from. We always skip this step, but remember where that actually comes from. It comes from the fact that we are square rooting both sides. Whoops. And the square root of x squared is actually equal to the absolute value of x, right? And if the absolute value of x is 2, then we know that the solution is x equals plus or minus 2. So the only reason we get that plus or minus in there is because of these missing steps that we always skip over, right? Just for the purpose of brevity. But they're still there, right? And so over here we need to do the same thing. The square root of x squared is actually the absolute value of x, only now we don't have an equation. But go back to Algebra 2 or pre-calculus, and think about what is the solution of an absolute value inequality like this? What is it? The absolute value of x is less than or equal to 2. What's the solution to that? X is what? Remember, we have to always trade for two cases, don't we? When we're solving an absolute value equation up here, we always said whatever's inside the absolute value, the argument is equal to the positive or it's equal to the negative, right? Okay, we're always set up two cases. Now, what are the two cases going to be here? It's going to be a compound inequality. Is it going to be an and or an or compound inequality? Which kind? It's going to be and, isn't it? Yeah, it's going to be and. Okay, there is a little trick for kind of remembering that I don't think I used this a couple of years ago, but it's kind of a good thing to think about now. There's a trick that goes keep it, switch, switch. So it's the KISS method. Keep it, switch, switch. So you know that if we get rid of the absolute values, the keep it part means I'm just going to keep everything the same. So one of my inequalities is going to be x is less than or equal to 2. The other one is going to be the switch, switch. So I'm going to get rid of the absolute values, but that means I'm going to switch the direction of the inequality and switch the sign of the number. So switch, switch looks like that. Now, what's the only way that I could build a coherent statement from that? X is less than or equal to 2 is one statement. X is greater than or equal to negative 2. Does that look like an and or an or inequality? That's and, isn't it, right? I mean, because if we're graphing this thing on a number line, I'm looking at that and that, right? When they're pointing towards each other like that, that means that we're looking for the captured intersection between the two. Okay, makes sense? Or to me, the way I always, if I hadn't done this in years, the way I would think about it is, I want to know the absolute value of x is really just the distance from 0 on a number line. Right? So the distance from 0 on a number line, if that's 0, if the distance from 0 is less than or equal to 2, it means I'm talking about places that are close to 0, right? It could be no further than 2. So that's telling me that it's an and interval right there, isn't it? Either way, though, the result is I'm getting x is greater than or equal to negative 2 and less than or equal to positive 2. And so that's my interval, right? That's the answer. Because that's what we got from this condition that was imposed on us. Okay? Give me 1 to 5 on that. How we doing? Okay? Or thumbs up, either way. Okay? All right. Okay, so today we're going to look at kind of the last discussion falls under continuity would be the intermediate value theorem, or IVT. This is another one of those what we call existence theorems in calculus, where we just have to meet some criteria, and if we meet the criteria, then the theorem guarantees the existence of something, and we got to go find it, maybe, right? But at least it tells us if it's worth looking. Okay? So what the intermediate value theorem says is that if I've got some function, and if the function is continuous on the closed interval from a to b, then if there is some value, let's just call it k, that is between the value of the function at a and the value of the function at b, right? So at a, if I evaluate the function at a, I get some output. If I evaluate the function at b, I get some output or some y value. So if there is some output value or some y value that's in between f of a and f of b, what do you suppose the intermediate value theorem guarantees? If the function is continuous, so I can draw it without picking my pen off the board, and if k is an intermediate value, right, it's between f of a and f of b, what do you think what's this going to tell us? Has to be true. Ah, okay. There has to be a value of the function equal to k, at least one, somewhere between a and b. Everybody buy that? Okay, so that's IVT. So here it is, right? It's an existence theorem again. Let f be continuous over a closed bounded interval a to b. If k is any real number between f of a and f of b, then there is a number c, is what we call it. There is at least one number c. This is wrong. I got to fix this. This is out of OpenStax, and they made a little mistake here. They probably fixed it, but that's a little mistake. This should be that. Should be in the open interval, a to b, satisfying f of c equals k. Okay? So between a and b, there's got to be at least one place where that's true. Okay? Might be multiple places, but there's at least one. Okay? Here is in the textbooks that are, I think, are on the way. This is kind of a cool thing they do in this book. And I think they do something similar in the Larson books too, the old books. The intermediate value theorem, it says essentially the same thing, right? Suppose f is a function that is continuous on the closed interval a to b, and f of a is not equal to f of b. They call it n, whatever. Different books are going to call it different things. If n is any number between f of a and f of b, then there's at least one number c in the open interval. They got that right. For which f of c equals n. Okay, this is kind of a cool little illustration of that, right? That makes this, it gives you something concrete to think about. To get a better idea of this result, suppose you climb a mountain starting at an elevation of 2,000 meters. Right, so you're starting down. I like this because a little backpacking kind of, as we head into winter, it's nice to think about summer activities. You're starting at an elevation of 2,000 meters and ending at an elevation of 5,000 meters. No matter how many ups and downs you take as you climb, at some time your altitude must be 3,765.6 meters, or any other number between 2,000 and 5,000. We just picked that one, right? But wouldn't you agree that you're going to have to hike through that altitude band at some point to get to the top, right? How does this meet the criteria of the intermediate value theorem? Is your position function continuous? If it's not, we got to talk, because you've got some abilities that are not normal. If you're able to just blink from there to there without covering every spot in between, then you've got some superpowers, right? Because most of us, our position function would have to be continuous, right? We have to move through space continuously, okay? And so, yeah, there's no way that we wouldn't have to pass through that band, okay? That makes sense? Okay. Now, when does that happen, or I don't know. Then that's where you have to go do a little deeper dive into the math. But the continuity theorem here is just telling us, yes, that must exist. Okay, so, and I don't know why. This is just the statement from the Larson book. It says the same thing. They just use k instead of n. Same thing, though. Okay, so let's try a couple of these. Let's show that this function has at least one 0. Okay? How could we prove that this function has at least one 0? F of x equals x minus cosine x. What do you think? How could we go about doing this? What are the two criteria that we have to meet for the intermediate value theorem to guarantee some value? What's the first one? Continuity. Okay, so on some interval that we're picking, it has to be continuous. So let's just look at that one right away. Is this function continuous? let's just pick, for now, let's just say on any interval, right? If not, we might have to be more specific. Are there any, is that function discontinuous anywhere? What do you think? Give me thumbs up, thumbs down. How you feeling on this one? Continuous, thumbs up. Not continuous, thumbs down. See, I'm seeing lots of thumbs up. Good. Okay, when we're dealing with a function like this, how do you think about this? It's x minus cosine x. We're looking for red flags, right? So we can look at each one of those pieces separately. We don't have to think about this as some complicated function. It's just a sum of two very simple functions, and we can look at them individually, right? Because all we care about is, do we see any red flags? Well, x is fine, right, by itself. That's no problem. Cosine x is fine by itself, and so the sum of x and negative cosine x should be no problem, right? Okay. So the answer is, yeah, this is continuous absolutely everywhere. So we can check off criterion number 1. Okay, what's the second part though? Right? We need to show that, go back, and we need to show that there's at least one number c in some open interval for which the value of the function equals n, right? Where n is some number that's between the value of the function at the endpoints of my interval. It's an intermediate value, right, compared to my endpoints. Okay, so really what we got to do here is we just have to figure out what some good endpoints would be for the interval then, because what's the value of n or k or whatever you want to call it? What's the value that we want to show the function is passing through? 0, right? If a function has a 0, then isn't that telling us that it's passing through the x-axis, right? It has a value where the function is equal to 0, right? So we know for part 2 that n equals 0, right? Or k, or whatever the heck you want to call it. So now we need to find values of a and b that would work, right? That are going to make 0 an intermediate value. So how are we going to do that? If n is 0, what could you tell me about the value of the function at a and the value of the function at b? What would they need to be for the intermediate value theorem to apply here? Okay, yeah, one would be negative and one would be positive, right? Because 0 would be between a negative number and a positive number. Okay? So can somebody come up with a value of, and does it matter which one? No, it doesn't. We just need to show that this function has, on some interval, the left endpoint could be negative and the right endpoint positive, or vice versa, it doesn't matter, right? Gabe, can you come up with a value of x where the output of the function is negative? Say it again. -1. Yeah, that works, doesn't it? That works, absolutely. And to be really safe, cosine swings between positive and -1, right? So the most that this could ever do is add or subtract 1 from this value. So to be extra safe, can anybody think of maybe even a little safer one that we don't even have to think about? Okay, -1,000,000, or how about -2, right? -1,000,000 would work though, you're right. If I pick -2 though, right, if x is -2, then the cosine could never push that up by more than +1, and so we know we're going to stay negative. Does that make sense? Okay, so then we could say f of -2 is less than 0. Do I care what it is? Not really, right? Not really. What's a guaranteed positive value output for f of x? +2, right? F of 2 is definitely greater than 0. So we meet our criteria, don't we? Right? Because n is between f of -2 and f of +2, right? Let's state that. So we meet our second criterion. And that's our proof. By IVT, there must be at least one place between -2 and 2 where this function has a 0. Okay? Doesn't ask us to find it, so we're done. Okay, give me thumbs. How are we doing on that? Okay. Okay, this one's going to be okay, read through that. And then vote with your thumbs. So the question is, can we use IVT to conclude that f of x has no zeros in the interval 0 to 2? Thumbs up or thumbs down? Got a thumbs up? So they're telling us it's continuous on the closed interval, and they're telling us that f of 0 is positive and f of 2 is positive. Okay? The question is, can we use IVT to conclude that f of x has no zeros in that closed interval? Okay, I got 3 thumbs up. 4. People still, some holdouts. Oh, there's 5. 6. 7. Okay, I'm going thumbs down. So we got. Yeah. Oh, go ahead, Gabe. You got an idea? Oh, okay. Yeah. I'll make it. You're right. I'll make it. I'll make it open. But even if it's open, I'm still saying. I'm still going thumbs down on this, right? Is it the job of IVT to guarantee that there are no zeros? No, that's not its job, right? Its job is just to guarantee when there are zeros. Can you guys think of a way? I mean, could we feasibly, we don't know what f of x is here, right? So could you think of a way, if that's 0 and that's 2, can you draw a function where that we have a positive endpoint there and a positive endpoint there, but it has zeros? Can you think of a function that would have zeros? I mean, is there a way I could draw a path from there to there and go through negative territory? Sure, right? Couldn't I just do this? Okay, so it could have zeros, right? IVT just can't guarantee that it has zeros because 0 is not an intermediate value relative to the endpoints. But they could exist, right? So don't overstep the bounds of an existence theorem. Existence theorems are just there to prove under certain conditions that something exists. They say nothing about where it can't exist or it doesn't exist. That's not their job. Okay? Okay, how about this one? Can we use IVT to prove that f of x equals 1 over x has a 0 on the closed interval from -1 to 1? Okay, vote with your thumbs here. What are we saying? Got a thumbs up? Another thumbs up? Another thumbs up? Another thumbs up? Another thumbs up? I think Lucy gave me a thumbs up. Ethan, thumbs up? I'm going thumbs down again. Going thumbs down again. Okay, well, now, I think you guys were looking at the second criterion. The second criterion, that looks good, right? F of -1 equals -1, and f of 1 equals +1. So that's good, right? It's an intermediate value. But what about the first criterion, right? Continuity. Is f of x continuous on the closed interval from -1 to 1? Where's it discontinuous? It's 0, right? Yeah, it's 0. This thing blows up. I have an asymptote at 0, right? So the answer is no. And because of that, we don't even really care about the second. If we fail one of the criteria, then we don't even need to worry about the other one, right? It flunked. So it flunked IVT. Okay, how about this one? Last one. Find the values of C guaranteed by the intermediate value theorem where f of x equals 18, if the conditions are met, right? I mean, if it applies, okay? So let's go through these. Thumbs up, thumbs down. Is f of x continuous on this closed interval from 5/2 to 4? Thumbs up, thumbs down. Okay, I'm seeing some thumbs up. Now you're getting nervous about this, aren't you? Okay, I'm seeing another thumbs up. Okay, yeah, I'm going thumbs up on this, right? Because where's the only discontinuity of this function? At 2, but 2 is outside of this interval, right? So on the interval, we're fine. We're fine. Yeah, so far so good. Okay, now we just need to check endpoints, right? We need to know, is 18 an intermediate value, right? Let's see. So if we evaluate the function at 5/2, we would get 55 over 2. Okay, so that's like, what is that? That's bigger than 25. And if we evaluate it at 4, we get 14. So is 18 between f of 5/2 and f of 4? Yeah, it is, right? But 18 is between 14 and something bigger than 25, right? Yeah. Okay? So yeah, so we know we know then that there is a value, right? So now we just have to go find it. So now we actually have to do something, right? IVT told us that there definitely is a value. Now we know we should go look for it. So how would we find this value? Is this fancy calculus? No, not at all. If we want to find where the function has an output of 18, what do? Set it equal to 18, right? Set it equal to 18 and solve. Okay, so what happens? If we set this equal to 18, okay, so talk to me about that. What are we going to do? How do we solve that? This is just algebra, but it's good. You guys are probably rusty on some algebra. You're going to be so good at algebra by the end of the year. I'll give you a hint. What do? Yeah, multiply by what? X minus 2. Good. Or cross multiply, however you want to think about it. Whenever you have a proportion, you have a fraction equal to a fraction, you can always just cross multiply, right? Even if this had been a fraction, I could have just cross multiplied. Okay? So I end up with x squared plus 3x equals 18x minus 36. And now I'm just going to put this in standard form, right, and solve this thing. Okay? So x squared, I'm going to get minus 15x, right? If I subtract 18x to this side, then I'll add 36. Now we're just solving a quadratic. So let's kind of briefly review. I know this is old hat, but let's think about strategically how we solve quadratics efficiently, right? If it's easy to do, we want to find magic numbers because that's the easiest thing possible, right? But if it's not easy to do, like if I had a coefficient of x squared that I couldn't divide away from both sides, you know, we probably don't want to mess with that. In that case, we'll probably just jump right into like quadratic formula or completing the square, right? Probably just quadratic formula, okay? All right, so can we find magic numbers that multiply to positive 36 and add to negative 15? We can, good. So what are they? X minus 12 and x minus 3, very good. Okay, so then we end up with the solutions, x equals 12 or x equals 3, correct? No. What was the original problem? Find the values of C guaranteed by IVT. So where is IVT guaranteeing values of C? It's very specific, right? Let's go back and glance at IVT one more time. Right? So if we meet the conditions, if f is continuous on the closed interval and n is an interior value, then there's at least one number c in the open interval a to b where the conditions are met, right? So IVT actually only guarantees, we're only looking between 2.5 and 4. So the only one we can keep is, now is that a solution? Sure it is, but it's just not, in the context of this problem, it's not what we're asking for, right? We're asking for the values guaranteed by IVT, and so that's the only winner. Okay, make sense? Okay. All right, last one, kind of a challenge for you. When are we out of here? 4 minutes. Okay, so I'll let you think about this one then. I'll put the notes up right away, so everything will be there. We'll talk about this, next time we meet, but see if you can come up with a solution to this. So at 8 a.m. on Saturday, a man begins running up the side of a mountain to his weekend campsite. And there's a little picture, right? On Sunday morning at 8 a.m., he runs back down the mountain. It takes him 20 minutes to run up the mountain, but only 10 minutes to run down. At some point on the way down, he realizes that he passed the same place at exactly the same time on Saturday. You see what I'm saying? Like when he looks at his watch, he realizes, oh man, yesterday at exactly the same time, I was at exactly the same spot. Okay, prove that's correct. Okay? Now you can do this proof. I'll accept a couple. You can do this by, there's a couple ways. You could just kind of provide a simple logical argument, or better than that, if you could apply the IVT. Okay? Okay, so think about that one. If you want to take a picture of that so you just can have it right on your phone, think about that over the weekend. That's your puzzler for the weekend. That's a pretty good little problem.